DraftScience video. Still can't hear. So, still can't get the physics working. But anyway, okay, so I found another Feynman video I listened to, the audio. It's a video, but it's mostly just audio, and some images relevant to the audio. So anyway, I'll post a link to that if I can find it. And it, wasn't terribly fascinating because it wasn't kind of big picture stuff. It was a lot of stuff about mesons and bosons and whatnot-ons. Some of it getting into some of the things. I guess Feynman earned some of his cachet, through making contributions on these subjects. One of them sort of sounded like my induction kind of argument regarding how things interact with each other, that they, induce a change in each other, and that change in each other induces more changes in each other. But anyway, so I've been thinking about the gravity thing, obviously, the one force, but I was thinking more just in terms of the, on the smallest scale, and just the exactly this kinetic thing, and this is a convenience to a certain kind of way of looking at it, that I would like it to work this way, but I know, okay, it probably doesn't work this way. And it also creates problems. So every time you come up with some idea to fix it, it's, it gets nuanced. Nothing critical to the overall theory, which is, I think, sound in the sense that it explains exactly, all this force dynamics is pretty direct, in terms of energy and identifying what has, what we're talking about when we say something has energy. We're just really talking about a directional imbalance, that this stuff is dominated by a certain amount of stuff going in a certain direction, and then we call that energetic. That's meaningful, but it's not big picture meaningful. It's not, how to put it. Well, anyway, so I've made this point before about accelerators, that accelerators aren't really adding anything to a particle or pushing it, literally. That they're basically just stretching it. They're changing its orientation, and they're creating in it an imbalance of directionality, so that it's now still held together, yet more of it's going in a certain direction. More parts are labelable. They can be labeled as quanta with vector A direction. And so when you give something more of quanta in A direction, that's the way it's going to go if it has more in that direction. And the accelerator is basically doing that. It's converting the proton, usually they use, I guess, and it's distorting it and changing it into energy, changing it into weakening its pattern, weakening its native condition, like stretching the solar system in a sense, but it's not really stretching because it's not even stretch. It's got more going in one direction than the other direction, so obviously it has to keep moving because it's got more things going in that direction. More stuff going this way than going this way, so it just keeps looping in a direction. Anyway, and so that's what, when you accelerate a proton, that's what you're doing to it. You're changing its configuration internally. You're converting its mass into direction. And so I came up with a, my version of E equals mc squared would be something like energy equals directionality. That energy is everything. All the quanta are energy. But you only recognize them. It's like the school of fish argument. School of fish, all the fish swimming around in one place. You could have 1 million fish swimming around each other, and the whole swarm doesn't go anywhere. But if all those fish decide to swim towards you, you're going to know that thing has energy. So no energy when they're swimming around each other, lots of energy when they're heading towards you. And so energy is just really a point where there's more stuff going in a direction. You know, that's energy. There's the collection would be here's a circle of directional arrows, and there's more of them going in a direction. Then that thing has energy. Alright, so the other thing I was thinking about is the Ising argument, the orbit argument, and just the strength, you know, the durability of something like a proton or something, where they can accelerate it, where they can distort it substantially, and it still retains some integrity as what it was. Just the fact that atoms are hard to break, most. They don't fall apart easily. It takes a substantial disruption. So another axiom would be that pattern, once it's created in the universe, patterns, they're kind of durable. It's not easy to unravel what's been raveled. A better way to put it, the relationships as they form get stronger, not weaker, you could almost argue. They get closer and closer. It's like almost like you could think about gravity, and as something gets in tight gravity, it gets harder and harder to pull it to wider gravity, or something like that. It's just that the relationship it's durable, that's all. There's durability, and you would just think, from my perspective, you know, once you break this down into just this directional arrow stuff, that it wouldn't take much to disrupt this relationship, the balance between these gravitational objects. But clearly it does take something substantial in most cases. Like I say, ions, different other things, kind of exception to that rule. But let's play with it a little bit. So I was thinking about one problem, and so this is minutia. This is not, well, whatever. This is what I've been thinking. So I just thought I'd do a video on it because that's what I've been thinking. So there's two ways again to look at this kinetic thing. So you could just say that two things come in. You know, two things have a direction, and what's happening is you know, this arrow and this arrow are interacting, but they're, you know, interacting in the sense that this arrow ends up going this way, and this arrow ends up going, this arrow ends up going this way, and this arrow ends up going this way, and it's a complete transfer. So the direction that this one was going, the Y arrow and the X arrow, you know, the X arrow ends up going this way, and the Y arrow ends up going this way, and that's one way of looking at it. You know, that there's a complete exchange of direction. And so, you know, that works for the propagation of light through space, because you can sort of see that nothing really changes. That whatever pattern you had here, so say you had a dot 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 pattern, that dot dot pattern is going to continue this way. Just, you know, it's not going to be stopped. Even though theoretically the photons are being knocked this way, they're really not, because the other photon's going exactly where it would have gone. And this works. It's just a way of exchanging direction. And if you have it in a, like I said, if you think of it a big picture kind of way, you know, going out, you can just kind of understand that the tendency would be overall. So if you had a bunch of arrows going in one direction more than they were going in the other direction, that you would shift stuff that way, but the stuff going this way would still be going this way. You know, patterns that were going that way would still be there. They would just be not where they were before. Let's see, that's a better way to put that. I don't like that. That never mind. Never mind what I just said. Forget that part. Let's just get back to what the argument I want to make. This does get a little complicated. So the thing I was thinking about was, what if, when you had this directional kinetic thing, they could just give away half of their directionality. So instead of giving away the full portion of their direction, then we gave away half of it. So this one would give away half of its down direction. And so this would still have half of its this direction, and so you'd end up with something going this way. But this one would also have the same scenario. This one would give up half and get half, and so you'd have both of them leave this way. So you have two that meet and they leave this way. Now this kind of thing, this idea of what happens, say, so the idea with gravity is there's a bunch of this extra arrows coming down this way that are blocked the arrows coming up this way, right? So that's what we're trying to analogize is the effects of gravity. So more are coming down than are going up, are reaching this little section of space. So this section of space has more arrows coming this way than has arrows coming this way, because of, say, the nucleus of the atom. And so this was an electron, let's say, getting trapped in an orbit. But the electron itself is doing the same thing as this is, because the electron itself is an orbital system. But anyway, but you can see how this tendency would, like, you know, the arrows are coming from all directions, so you have to understand that, would likely be an easier way to create the, you know, this circle pattern. With this theory, you know, with the all direction is exchanged, you end up with something very complicated. So you have an extra arrow comes down this way, and this is something orbiting this arrow. So what you have is the exchange, which means this arrow goes down, and this one flies out nowhere. Okay, it goes that way, and you'll never, it won't be kept by the thing. But this one, this arrow is heading now towards the nucleus, let's say. So now we're getting the idea of the least circle, you know, where the thing is orbiting, but it's so the point I'm making is that when something's orbiting in an atom, it's not orbiting in a kind of nice least pattern. It's got a very ugly pattern where it might travel quite a distance down before it gets directionally changed in that direction, and then it could be directionally changed up, and then it could be directly changed over, and then it could be directly changed the opposite way. And so it could have a very you know, loop-de-doo kind of way, but the tendency would be that through all of this nonsense it would still end up orbiting. It just, obviously, this time it would take to get around here couldn't be anywhere near the speed of light, because it's traveling so much distance. So there'd end up being an awful lot of distance traveled to get there. So that's something I have to consider is, you know, what percentage of the speed of light do the fastest things orbiting go. I knew that at one time, and I don't know it now. Because that'll tell you something about how eccentric those movements can get. But we really don't know, because we don't know, we have no way to trace or track what's going on inside of, say, an electron. So an electron, I'm saying, isn't just a ball, a hard thing. An electron is an orbiting things, quanta orbiting, and specifically, usually configured through the acquisition of photons being absorbed. But regardless, but the idea would be is that it's the stuff going around it is going around it probably very slowly, in the sense that the gravity is very uneven. You know, held together in this very yin-yangy, bouncy, vibraty, horrible way. Because you have to understand, for every tug one way, you know, for every change in a direction, it changes the likelihood of a change on the opposite side of that. So another thing I wanted to kind of get to was the idea that gravity sort of has a, you know, it doesn't get absorbed by things. So say two things are gravitationally related to each other, this gravity magnifies. So they add, their gravities sort of add to something out here. So something out here will be affected more when these things are lined up. This overall mass is higher. And when they're not lined up, say if they're sideways, then the gravity here at this point would be weaker. So that's sort of an interesting way to look at this, is that gravity has moments or periods where it's stronger and weaker based on just the orbiting of the stuff. Like in the solar system, sometimes the planets kind of line up, and when they line up, the gravity at the point, that maximizes that alignment would be stronger than it would be when they're not aligned. And so anything that would fall into that point, cross that point, would be affected by a stronger gravity. And so it could change whether something gets captured or not captured based on alignment issues. But it kind of makes this idea of gravity turning on and off, in terms of its strength, depending on that configuration and who's orbiting who's moving more, velocities and all that kind of stuff. So anyway, I haven't really gotten to the point I wanted to get to, which is so even with the crudest system, this all or nothing, which I think it has to be. I think it has to be a complete directional exchange, just to explain how light gets across the universe without. So if you have this idea where they could add, then a photon would have no way of surviving its travel through space, because it would actually get moved. The pattern, like the photon I'm claiming is made up of two elements, two quanta, at least. A stream of quanta separated by a period. And there'd be no way to keep that coherent, because one might move this way, and then it moves that way, and then it moves and it's just going to get, it's the amount of movement would be too, so I want to say it would be too excessive, but I mean, in the end, it doesn't really matter. So again, I have to argue, maybe it is possible. See, you could argue that even if it changes direction this way, because there's an equal number of arrows in the end, there's the same number coming from this side, theoretically, as this side, it's just always going to keep going straight. But the trick is, see, with this, it doesn't matter, because you'll never move it sideways. But this you could if you had gravity. So light would be gravity sensitive under this pattern. Because if you had more arrows going from this way, then you'd have a tendency to push the light this way more often, and you'd definitely have the light move over in a direction. And how much each photon, each quanta moved could be different. So the light would end up being weak by not being lined up anymore. So that, I don't think, can be the way it works. I think the kinetic has to be all or nothing. You give away all of your directional information. You exchange all of it. And so I'm just saying the implications of that are, so it just gets kind of complicated. It's really the same thing force-wise, but I just mean it does get kind of complicated when you're trying to create this orbit. So you have the thing traveling this way, and it's got to go in a circle to stay in the orbit. And then it gets knocked down by gravity, so it exchanges. This one goes away. This one stays, okay, in the realm of possibility as gravity. So you sort of have to argue that these ones leaving sideways, though, could actually, from another atom or another element, come in here and knock this one this way. And so that restores your Elise. But obviously they're also doing that at the bottom here in the opposite direction. So you have just as many free arrows going that way as you have free arrows going that way. But the end is, again, you have to look at this overall, what happens in the end. And in the end, there would be a balance. It's just to get to that balance, you'd have to assume that this could end up doing something like this, and like this, and like this, and then like this, and then like this, and then like that, to get to finally its point over here. So to get from here to here, it would end up doing something rather eccentric. But the probability is it will end up over here through all the interactions because of just the net force effect. The net amount of directional information being exchanged will inevitably end up over here. It just won't end up over here in this nice orbiting pattern. So with these big objects in the solar system, we have the illusion of the smoothness of these curves because we're watching a whole giant thing move, which averaged everything out. But the individual atoms and the individual protons, neutrons, and electrons of the thing are the thing getting affected by the actual gravity. And those things, those bits, are doing a lot of moving to get from here to where the thing ends up. They're not traveling in any straight lines. Well, they're traveling in straight lines, it's just that their lines are real tiny little straight lines. So I guess that's sort of the point, is that it's all straight lines, so there's no true curves. You know, that's where pi will finally fall apart, is that there's no curve in the fundamentals of the universe. There's only directions, vectors. No, and it's a straight line from point A to point B. It's just that point A to point B is sometimes a very tiny distance. So I don't know if I really gave you a feel for what I was, what was bothering me here. But it's just this kinetic thing is sort of interesting. Like I said, because you have these two ways to look at it. As a partial exchange, an equal exchange of half of the information, or a full exchange. The half exchange makes orbits more sensible, and the full exchange makes propagation of energy through space more sensible. That it stays coherent, that photons can travel across the entire universe without being without the pattern, the period information being destroyed. And I don't think they could do that, just because of all the little subtle gravitational effects. I don't think they'd ever get here in one piece, so to speak, if this partial thing happened. So it just makes it more complicated to think about how this could be a strong nuclear force. I mean, this seems so, like, almost so arbitrary that a piece of the electron could end up going in the wrong direction and fly right the hell out of the electron. But you have to understand, for every change in direction that allows that to happen, there's all these other changes that are taking place, the exchanges, and the tendency is always going to be in one direction. So the tendency is going to be neutrality in all effects except for the one in the directional that you have extra direction in. And so it will always regain its, the balance will still be 99%. It's only that 1% vector that's changing. This 1 o'clock, this 12 o'clock position is the only position that matters. It's changing. All these other positions, all these other influences will balance out to be exactly the same as they were before. It's only this one direction where you've changed the directional information. So in net, all you're going to do is exchange this directional information will subtly be imposed on this whole thing and subtly change its position in the end here in this direction. All of this will end up being subtly moved in this direction, but it'll be done through this convoluted Aliasing, this convoluted probabilistic, in the end it'll end up being okay kind of gravitational relationship between bodies. So again, the other thing you have to understand is the gravity that's holding this thing here is the gravity being shared by some other object that's balancing it on the other side here, in all likelihood, especially for an electron. This is what's holding it together, this bond. So as this thing moves closer, this gravity is getting stronger, which is going to tend, to block things that are pushing this, it's going to block the stuff coming this way, which means this thing is going to tend to move in this opposite direction. So they're both getting closer to each other, and so it's almost like the idea that, when you bring two bodies closer and then they swing out, so it's like it comes in, they rotate around each other and they go wide, and so it's almost like the way comets travel. It's going to go wide, and it's going to go wide, and it's going to go wide. And so that's what's sort of happening inside of an electron, is that there's no round orbits. There's orbits created by gravity getting stronger, gravity getting weaker, gravity getting stronger, gravity getting weaker, based on the fact that stuff will end up moving towards the other thing in a way, then they'll be driven closer to each other, but not close enough to hit each other, and that'll just cause them to spiral in a direction that'll be exactly opposite, opposing their gravity. But those blocking forces will again drive them back together again. Because their gravity isn't connected to them, it's connected to, that's the other thing. That's why you have to have the four objects kind of argument. So it's like you have two separate things rotating, and this one is creating gravity for this one, and this one's creating gravity for this one. So your pairs are, the A is tied to the C, and the D is tied to the B. So their gravities are non-reciprocal. So when this one comes in, it's affecting this other element, which could be transverse to the first one. So what if they were transversely orbiting? Then you could really get the idea that when one goes in, it would have a different effect depending on what cycle the other one's in. So if one's in its wide cycle and this one's in its narrow cycle, narrow, close, that this one's moving towards when this one's going out, so that one's helping, bonds, and so they end up just pushing the two wobbles in the same direction. Well, anyway, I'm just saying that that's what complicates this. So yeah, I want to try to start adding some math to this in terms of quantizing. But yeah, I haven't figured out how exactly to do that. I imagine just establish a value, and then figuring out what proportion of gravity is necessary, what proportion of directional change is necessary to change an atom's movement to give it velocity, in which you can establish how much energy it takes to, say, move a hydrogen atom, 1 Planck constant of distance. Then you can start doing something. But anyway, I just thought of something and I forgot it. Something rather important. I'm feeling a little poorly lately. Anyway, yeah, I think that's it. I thought there was something else I wanted to get to. So, the additive thing of gravity is sort of interesting, the way the little bits add up. And that the more stuff that gets stuck to each other, the more likely it is to collect stuff. And that's sort of another interesting conversation, is just this whole conversation of how densely packed something can get. How big can something by mass get before it ends up blocking so much stuff that the stuff in the middle can't get any more gravity. Not enough gravity can get to the center because it's so dense. So just imagine the Earth is, a zillion times bigger, or whatever, 1,000, million times bigger. the argument would be is that the thickness of the of the radius of the Earth, the thickness, would be blocking so much gravity that the atoms in the center would start to fall apart because they can't be maintained. They don't have enough gravity, so those atoms would start to degrade. And so is born a sun, let's say. So first it goes nuclear, and then it burns the atoms. So you could almost argue that the Earth could become a sun if it got big enough, because the internals, the matter in the middle, would end up turning into hydrogen, because the atoms would start getting more and more unstable. So it would start turning heavy matter atoms into hydrogen. It would do the alchemy thing. It would break everything down into hydrogen. So it may not be a coincidence that suns are made out of hydrogen, in that they were origined that way. It just might be that they convert back heavy elements back into hydrogen, because they become so unstable because of the incredibly high pressures created by their high gravitational blockage. So they're blocking so much gravity that the matter inside of them can't be sustained as matter. And then eventually they supernova or whatever, because there's no way to contain. Even the hydrogen atoms just start blowing up. They don't just degrade a little bit, they degrade a lot, and it just blows up. Nuclearizes. Nuclearize. Yeah. Might be a word. Yeah. So that's what an atomic bomb is doing. It's nuclearizing. Particularizing. Nuclear particularizing. Well, fuck it. No point making too many new words. Alright, so I think I've done what I had to do here. Gravity additive. Yeah, I did want to get to the no true reflection argument too, because there was a little bit of that. Feynman often talks about it, and it just doesn't seem to say that clearly enough or often enough. He's bouncing off. Yeah, use that kind of terminology in describing particle accelerators and the byproducts of what they're observing. And he uses the word like bouncing off. I just don't think that's accurate. I just don't think things bounce off. I don't think there's any such thing as a bounce off. You have to, like for spaceships. Spaceship goes into space. It can't bounce off of the new moon. What it has to do is get captured in the moon's gravity and then change its, acquire an opposite direction or a different direction. But there's no bouncing off of objects, gravitational bodies, things. Yeah. So I just think that's not the right answer. So anyway, enough said. So until next time.